Imagine for a second that you're looking at a beautifully detailed photograph of a really complex microscopic machine.
Like a high-def snapshot.
Yeah, exactly. You can zoom in, you can map out every single gear, and you can point to it and say with total confidence, there it is. That's how it works.
Right.
And that static perfect snapshot is basically what artificial intelligence, like the famous AlphaFold, gives us today when we look at proteins. It's very comforting. It feels incredibly precise.
Oh, absolutely.
But what if I told you that photograph is lying? Or, well, at least hiding the most important part of the truth.
Yeah, it's leaving out the best part.
Exactly.
Yeah.
So welcome to a brand new deep dive.
Whoa.
Today, we are exploring what you might call the dark matter of structural biology. We're talking about the hidden, completely invisible movements of proteins.
It's such a fascinating topic.
It really is. Our source material today is a groundbreaking Nature paper. It's titled Large-Scale Discovery, Analysis, and Design of Protein Energy Landscapes. And our mission for this deep dive is to figure out how scientists are finally mapping the unseen breathing, I guess you'd call it, of thousands of proteins all at once, and why this is the missing puzzle piece for AI in biology.
It really represents a massive paradigm shift in how we think about life at the molecular level, honestly.
Also,
Well, we've spent years celebrating AI for giving us the native state of a protein.
right, the lowest energy, most stable 3D form.
Exactly. But that native state is essentially just a statue. If you actually look at proteins in reality, like inside a living cell, they are continuously fluctuating.
You're twitching and moving around.
Right. They're unfolding and morphing into these higher energy excited states.
And because these excited states are so rare, and they happen in, what, a fraction of a second?
Sometimes even faster, yeah.
Yeah. They've been completely invisible to traditional structural biology. But from what I read in the research, those invisible flutters are doing a massive amount of heavy lifting.
Oh, they dictate everything. They control how proteins actually function in our bodies, how they interact with pharmaceutical drugs, and
terrifyingly, how they accidentally clump together to cause aggregation diseases.
like Alzheimer's, right.
Yes, exactly. They even control how our immune systems decide whether to attack a molecule or just leave it alone. The native state is really just the protein's home base.
It's where it spends most of its time.
Right. But those rare, invisible excursions away from home, those dictate its actual real-world behavior.
So why are we just mapping this now?
The problem has always been a bottleneck of measurement. Until this specific research, mapping these shifting energy landscapes was agonizingly slow. I mean, you had to isolate one single purified protein, put it in a highly controlled environment, and just watch it.
Wow. One at a time. Yeah. But what we are looking at today is a new multiplexed method that completely shatters that limitation. It lets us watch thousands of proteins breathe in the dark, all at the exact same time.
Okay, let's unpack this. Because before we get to the massive scale-up part, we really need to understand the core concept of an energy landscape and, how you even measure an invisible flutter in the first place.
It's tricky to visualize.
Yeah, so I want to try an analogy. Imagine a protein not as a solid bronze statue, but more like a bustling, slightly drafty house.
Right.
Most of the time, the house is completely closed and locked tight against the weather.
Right, and that closed house is your folded native state. What's fascinating here is how well that actually maps to the biochemistry.
Because the delicate interior is protected.
Exactly. Because the house is closed, the delicate interior, the hydrophobic core of the protein is protected from the outside environment.
Right. But then, the wind kicks up. Randomly, a window blows open for a split second before slamming shut. Or maybe a whole wing of the house flings open.
Which would be a partially unfolded state.
Exactly. Or, in a really rare storm, the entire house just completely collapses into a pile of lumber, and that would be the globally unfolded state.
Perfect analogy, yeah.
But if these open states are happening so incredibly fast, how do we catch them in the act? The paper talks about this molecular spy called hydrogen deuterium exchange, or HDX. How does that actually work?
Let's stick with your house analogy. Imagine we submerge this drafty protein house in a literal flood of heavy water.
Heavy water meaning today's dollars.
Right, water where the normal hydrogen atoms are replaced by deuterium, which is just a heavier isotope of hydrogen. Now, the structural beams holding your protein house together are made of hydrogen bonds.
Oh.
Specifically, these bonds involve the backbone amides of the protein chain. As long as the house is closed, those amides are safely locked away from the heavy water flood.
But the moment the wind blows a door open,
The heavy water rushes right in. The moment a structural element fluctuates into one of those higher energy excited states, it gets exposed, and the chemistry just naturally ticks over.
so swaps.
Exactly. The protein instantly swaps out its normal hydrogen atom for a heavier deuterium atom from the surrounding water.
Oh, wow. So the heavy water really is like a spy. It's infiltrating the protein and leaving a literal weight behind. A heavier atom, every single time a specific part of the protein lets its guard down.
Yes, and because deuterium is heavier, we can literally just weigh the protein later to see exactly how many times the door blew open.
That is so clever. But there's a piece of the math in the paper that kind of tripped me up. They talk about the thermodynamics relying on something called the EX2 assumption. What does EX2 mean, and why does it matter?
Yeah, the EX2 assumption is really the mathematical heart of this entire technique. You have to think about two things happening when a protein breathes.
Oh, what are they?
First, the protein structure physically opens and closes. That's the fluctuation. Second, the chemical swap of hydrogen for deuterium actually happens.
Right, the structural opening and the chemical swap.
EX2 assumes that the closing of the protein is drastically faster than the actual chemical exchange.
Wait, so the protein is fluttering open and shut constantly, but the chemical swap is the bottleneck.
Exactly. Because of this specific dynamic, the exchange follows first-order kinetics. The chemical exchange rate, we call it dollars, is highly dependent on the pH of the water.
So because we know the chemical speed limit based on the pH, we can measure the actual observed weight gain, the Chemolyte-Shix-Alders, and then just work backward.
You've got it perfectly. By measuring how fast the protein actually takes on that heavier deuterium spy, the researchers can calculate the exact opening free energy, which is represented as delta G open.
And that value is a direct measure of stability.
Yes, a tightly locked region of the protein requires a massive amount of energy to pry open. Because it rarely opens, it takes in that heavy deuterium spy very, very slowly.
Whereas a wobbly, unstable region opens constantly.
Right, and it swaps its hydrogen almost instantly.
Okay, so let's do a quick recap for you listening. Number 1, proteins aren't static, they breathe. Number 2, we track this breathing by dunking them in heavy water, which acts like a molecular spy, leaving heavier atoms wherever the protein opens up. And number 3, by tracking the speed of that weight gain, we can map the exact energy landscape of the protein.
That's a great summary.
So here's a question for you, the listener. Can you imagine trying to track this hydrogen-swapping spy game, not just for one protein, but for thousands at the exact same time?
Which is exactly what they did.
Right, because earlier we talked about how doing this for one single protein used to take forever. But the title of this paper promises large-scale discovery. How did they go from tracking one drafty house to tracking a whole city of them at the same time?
This leap in scale is what makes this a landmark paper, truly. To train the next generation of AI to actually predict these dynamic movements, a handful of examples just won't cut it.
AI needs massive data sets.
Right, library-scale data sets. They needed a way to multiplex the process.
Here's where it gets really interesting. The researchers developed a pipeline called mHDX-MS. That stands for multiplexed hydrogen deuterium exchange mass spectrometry.
That's a mouthful.
Yeah, but to visualize this, think about traditional HDX like tracking the intricate, specific dance moves of one person alone in a really well-lit room. You can clearly see every step.
Yeah, very easy to track.
But what this team did is turn off all the lights, cram 1,000 different dancers into a crowded club, and try to perfectly map every single twitch of every single dancer simultaneously.
Which sounds impossible.
It does. How is that physically possible in a laboratory?
It all starts with synthetic biology. They didn't purify proteins one by one. They started by synthesizing massive DNA oligopools.
What does that mean in plain English?
Essentially, printing a vast mixture of DNA sequences that encoded up to 100 and 334 different small protein domains, all mixed together in one tube.
And these are small domains, right?
Yeah, ranging from 28 to 64 amino acids long. They took this massive DNA library and expressed it entirely within a single flask of E. coli bacteria.
So they just brewed a total biological soup of over 1,000 unique proteins at once.
A highly complex soup, yeah. They purified that mixture, keeping all the proteins together, and then they flooded the entire club, to use your analogy, with the heavy water.
Wow.
And to capture the full dynamic range of movements, they exposed the soup to the heavy water for 64 specific time points.
64 different snapshots.
Right, starting at a mere 25 seconds and going all the way out to a full 24 hours.
Wait, I also noticed in the methodology they ran this entire 24-hour time lapse at two totally different pH levels, like pH 6 and pH 9. Why dunk the proteins in different acidities? Does the pH change how fast the doors of our house blow open?
That's a great question, but no, it doesn't change how fast the doors open. It changes how fast the molecular spy operates.
Oh, this goes back to that EX2 assumption.
Exactly. The chemical exchange rate is dependent on pH. By running an experiment at pH 9, they drastically speed up the base-catalyzed chemical exchange.
So pH 9 forces the spy to work at hyperspeed.
Right. This allows them to capture the incredibly slow, highly stable structural openings that might otherwise take months to measure at a neutral pH. We just speed the spy up to catch them.
Ah, okay. And pH 6?
Running it at pH 6 slows the spy down, which lets them accurately measure the extremely fast, unstable flutters that would normally happen way too quickly to track.
So combining both gives them this huge range.
Yeah, a staggering 1,000,000-fold dynamic range of measurement.
That is just brilliant chemistry. But it sounds like a literal data nightmare. I mean, you have a soup of thousands of different proteins, all gaining different amounts of weight across 64 time points at different pH levels. How do you untangle that?
You definitely can't just put that on a normal scale. You need a very specialized instrument. The computational pipeline they built is centered around something called LC-MS-MS.
Which stands for liquid chromatography, ion mobility mass spectrometry. Let's bring back our crowded dance club analogy. How does this machine act as the bouncer to sort out who is who in the dark?
So the bouncer uses a 3D coordinate system to uniquely identify every dancer in the club. We call it a 3D tensor.
Okay, what's axis 1?
Axis 1 is retention time from the liquid chromatography. This is essentially asking, when does the protein physically exit the column? Or, in our club, at what exact minute does the dancer walk out the front door?
Got it. Time of exit. What's the second axis?
Axis 2 is drift time from the ion mobility.
How does that work?
This measures how fast the protein physically flies through a tube of inert gas. It's based entirely on the protein's aerodynamic shape.
Oh, interesting.
Yeah, a tightly folded compact protein flies through the gas very quickly. A more unwound floppy protein drags, so it takes longer.
So our bouncer is sorting the dancers by their physical shape and how they move through the crowd. And the third axis has to be the mass, right? Since we were tracking the heavy water weight gain.
Correct. Axis 3 is the mass-to-charge ratio, the raw weight of the protein.
Why do you need all three?
Because in a soup of thousands of proteins, many of them will weigh the exact same amount. Mass alone just isn't enough. But even if two proteins share a mass, they will have different aerodynamic shapes, or they will exit the column at different times.
The 3D tensor pulls them apart.
Exactly.
So you have this massive 3D grid separating every single protein. But you still have to calculate the invisible energy landscapes for all of them. How does the computer actually do that math?
This is where Bayesian inference comes in.
Okay.
The algorithm looks at a specific coordinate in that 3D grid, and it tracks how the mass at that exact spot increases across all 64 time points.
So watches the weight go up.
Right, and it uses Bayesian probability to infer the exact set of individual opening rates for every single exchangeable hydrogen bond in that specific protein.
That is a lot of math.
It is. They even had to build a custom path optimizer algorithm just to make sure they were tracking the correct expanding mass envelope as the proteins got heavier and heavier over the 24 hours.
Okay, so a quick recap of the scale here. They synthesized massive libraries of proteins in one batch. Then they used this 3D tensor machine tracking time of exit, aerodynamic shape, and mass to sort them all out. And then they used Bayesian math to map the landscapes.
Precisely.
So out of an initial pool of over 15,000 sequences, they successfully mapped the landscapes of 5,778 distinct protein domains.
Which is an ocean of new data.
Right. Which brings me to the most pressing question. When you finally lay out thousands of these invisible energy maps side by side, what do you see? Like, here's a question for you listening. If two proteins look identical on the outside and take the exact same amount of energy to completely destroy, do they behave the same on the inside?
If we connect this to the bigger picture, the data revealed a profound disconnect in how we traditionally understand stability.
Really?
Yeah, we have to draw a hard line between global stability and local fluctuations.
Break those down for me.
Global stability is the massive amount of energy required to completely unfold the entire protein. We call it delta gunfold. Local fluctuations refer to the average energy of the smaller partial openings, which they call delta GAV.
Oh, this sounds exactly like our house analogy. It's the difference between a massive hurricane blowing the entire house down that's global stability versus a draft just blowing open one specific window, which is local stability.
Exactly. In classical biophysics, there's this comforting concept called the ideal two-state model.
What does that mean?
A perfect two-state protein is highly cooperative. It behaves as an all-or-nothing system. Either the entire house is perfectly folded and locked tight, or the entire house is completely blown down.
There's no middle ground.
Right. If a protein is globally stable, the assumption was always that all its internal parts were also locked down tightly.
But the mHDX-MS data proved that assumption wrong, didn't it? The paper highlights that massive amounts of proteins exhibit low opening cooperativity. What does a protein with low cooperativity actually look like when it breathes?
It looks like a house where the main walls are standing, but entire sections of the roof are constantly rotting away and reforming.
Wow.
Yeah, in these proteins, the global structure holds together, but specific secondary structures like an entire alpha helix or a beta hairpin are secretly unraveling. They expose their internal core to the heavy water at very, very low energies.
The paper specifically points out the Lion's M and SH3 protein families as culprits for this. They found domains where the overall 3D shape was incredibly stable, but underneath the surface, huge regions were just a wiggly, unstable mess.
Yeah, the energy profiles literally cross over on the graphs. One protein might be much harder to destroy globally than a second protein, but infinitely easier to unravel locally.
And this is the critical blind spot of our current AI models, right?
Oh, completely. This hidden variation is entirely invisible to AlphaFold.
Because AlphaFold just predicts the static shape.
Right. It looks at those two proteins and says, yep, they have the same stable shape. But on the inside, one is a rigid, all-or-nothing fortress, and the other is secretly leaky and constantly exposing its delicate internal structure to the environment.
And I mean, this isn't just academic trivia. If you are a pharmaceutical scientist trying to design a new protein drug, or an engineer making a synthetic enzyme for a factory, a leaky protein is a total disaster.
It's the worst-case scenario.
When parts of a protein unravel, the exposed hydrophobic core gets sticky. It clumps together with other proteins. In medicine, that stickiness is what causes side effects. It's what triggers unwanted immune responses.
And it's the literal mechanism behind devastating aggregation diseases. You desperately need to know if half of your custom protein naturally unravels in the dark.
Okay, so to recap section 3, global stability does not equal local stability. Some proteins secretly have wildly unstable, wiggly parts, even if the overall structure holds together. So listener, if you were designing a protein drug, wouldn't you want to know if half of it naturally unravels and clumps up?
Which raises an important question, and it's the final major hurdle the researchers tackled. It is an incredible breakthrough to simply find these hidden, leaky, weak spots using this dataset. But observation isn't enough.
Can we actually fix them?
Right. Can we take this data and actually engineer the energy landscape?
So what does this all mean for the future of protein design?
Yeah.
How do we transition from just using our heavy water spies to take measurements to actually becoming microscopic architects? Can we reinforce those wobbly bricks without accidentally changing the overall shape of the fortress?
To achieve that, the team turned to machine learning.
Of course they did.
Yeah, they took their newly minted massive data set of opening energies and computationally analyzed over 4,500 different structural features for every single protein.
What kind of features?
They analyzed the sequence, the compactness of the folds, the number of specific amino acids like proline, the electrical charge, the helices, literally everything. They trained the AI to uncover the hidden grammar of protein dynamics.
They wanted to know why.
Exactly. They wanted it to learn exactly why certain structural features lead to low cooperativity.
They were looking for the biochemical rules of wobbliness. And once the AI learned those rules, did they try to patch a leak?
They did. The paper highlights a brilliant case study. They looked at a completely de novo designed synthetic protein named HHRD40518.
Okay.
It's a small protein made of 3 alpha helices bundled together. Now, globally, this synthetic protein was highly stable. AlphaFold predicted a beautiful, tight, perfect structure.
But the heavy water spy revealed the dark secret.
Right. It suffered from terrible low cooperativity. Specifically, its third helix, which they named helix alpha 33, was highly unstable.
It was the leaky wing of the house.
It was constantly unraveling and exposing its interior while the rest of the bundle stayed totally intact.
So armed with their machine learning insights, how did the researchers fix that specific helix without ruining the rest of the protein?
They introduced a highly targeted double mutation referred to as R35DG45L.
Okay, let's break that down.
They surgically swapped 2 amino acids. At position 35, they swapped an arginine for an aspartic acid. And at position 45, they swapped a glycine for a leucine.
Let's look at the physical why behind those specific swaps. Why would swapping those 4 microscopic building blocks stop a helix from wobbling?
It comes down to basic chemistry and physical space. Arginine is positively charged, while aspartic acid is negatively charged. By putting an aspartic acid at position 35, the researchers likely engineered a tiny magnetic lock, a salt bridge that pins the helix to the rest of the protein.
That makes perfect sense. And the second swap?
The second swap is all about flexibility. Glycine is the smallest, most flexible amino acid. It literally acts like a hinge.
Which is terrible if you want a stiff, stable helix.
Exactly. By swapping that flexible hinge for leucine, which is bulkier, much less flexible, and loves to pack tightly into the water-fearing core of the protein, they essentially wedge the helix firmly into place.
It's like taking out a rubber band and replacing it with a steel bracket. Did it actually work?
It was a total triumph. The global, visible shape of the synthetic protein remained exactly the same. But the invisible internal wobbling was completely neutralized.
Whoa.
That specific wobbly helix, alpha-3,3-dies, was stabilized by an impressive plus 1.2 kilocalories per mole. The entire protein became vastly more cooperative, behaving much more like that ideal all-or-nothing fortress we talked about.
And I saw they didn't just trust their own multiplexed mass spectrometer. They took this newly engineered, non-wobbly protein and validated it against traditional gold standard nuclear magnetic resonance, or NMR.
Right, and the NMR confirmed it perfectly. They didn't just observe the invisible physics of the protein, they actively edited it.
So a final quick recap. Massive data collection led to machine learning insights, which led to the precise, successful engineering of a protein's invisible energy landscape.
It proves that the energy landscape is programmable. We now have the tools to gather the training data, the machine learning models to decipher the rules, and the chemical understanding to physically patch the leaks.
Which brings me to a final thought for you to mull over as we wrap up this deep dive. We started out talking about photographs and static snapshots. AlphaFold and modern AI give us the breathtaking ability to predict the physical static shapes of proteins.
Which is huge.
It essentially solved the native state problem, which is one of the greatest scientific achievements of our time. But as this research proves, that static shape is only half the story. The statue is breathing.
And it is the breathing, the dynamic misbehaving in the dark, that ultimately drives the biology of health and disease.
So here's a question for you. By proving we can engineer not just the shape of a protein, but its invisible motions, how might this change the way we approach curing diseases? The next great frontier in biology isn't just about predicting what a protein looks like. It's about predicting how it dances, how it breathes, and how it fluctuates.
It changes everything.
It makes you wonder, could the future of medicine be designed not just to fit into a protein's physical shape like a key in a lock, but to actively tune its energy landscape? Could we design a drug that physically dampens the dangerous, wobbly vibrations of a disease-causing protein, stopping Alzheimer's plaques or immune triggers before they ever have the chance to start?
We are firmly transitioning from an era of static structural biology into an era of dynamic biology. The possibilities for therapeutic design are limitless once you can see the whole picture.
It's incredible to think about. Thank you for joining us on this deep dive into the hidden lives of proteins. We hope you walk away looking at the biological world a little differently today, not as a collection of static, perfect machines, but as a shifting, dynamic, breathing landscape. Keep questioning the invisible forces shaping our world, and we'll see you next time.